um, Dr. Dieter Potts. And so if you'll indulge me, I'll give a little bit of an introduction. So Dr. Dieter Potts is the Senior Director of Robotics Research at Nvidia and professor in the Paul G. Allen School of Computer Science and Engineering at the University of Washington, where he leads the UW Robotics and State Estimation Lab. Dieter obtained his PhD from the University of Bonn, Germany. His research is in robotics and artificial intelligence with a focus on state estimation and perception, applied to problems such as mapping, object detection and tracking, manipulation, and activity recognition. He has published more than 200 technical papers and is the co-author of the textbook Probabilistic Robotics, which I'm sure a lot of us are familiar with. He is a fellow of the IEEE, the AAAI, and ACM, and a recipient for the 2020 Pioneer of Robotics and Automation Award. Dieter also received several Best Paper Awards at the major robotics, AI, and computer vision conferences. He was the editor of the IEEE Transactions on Robotics program co-chair for the 2008 AAAI Conference on Artificial Intelligence and program chair for the 2013 Robotics Science and Systems Conference. And so with that, Dieter, please take it away.
All right. Can you see everything working out? Great. Thank you so much for inviting me. I just checked actually, my last visit was almost exactly 8 years ago. So it's clearly overdue that I'm coming back. And I remember it was great. So of course it would have been much nicer today to do this in person, but under the circumstances, I guess that's as far as we can get. Yeah, and thank you so much also for the very kind introduction. So I am currently on a kind of half and half position where I'm spending half my time at the University of Washington and the other half at Nvidia. I joined Nvidia about a bit more than 3.5 years ago to start a robotics research lab in Seattle. And today I'm going to talk mostly about some of the work that we've done in this lab over the last years. So the mission of the work we're doing is really kind of in the context of robot manipulation, where we are doing the basic research that enables the next generation of these manipulators that can operate in complex dynamic environments and collaborate with humans to solve longer term complex tasks. Application domains are, of course, on the one hand side in, let's say, flexible industrial manipulation tasks, but also, I think, specifically in the healthcare sector, helping elderly people in the home is where I think this next generation of robots can have a very, very positive impact on our society. And of course, ultimately, I guess we all want to have a robot in the home that's going to help us with certain duties, but I think we're actually still pretty far from having viable solutions for kind of doing many tasks in the home. But that's kind of the goal. So we want to look at the basic research still. So we publish the research that we're doing. We're collaborating with universities and also have many interns. So the work that you're seeing here is mostly, of course, done by some of the great interns we had over the last years. So when we started the lab, we wanted to see that we're not only looking at like small isolated components, but also kind of a task that requires integration of different kind of techniques into a single system that can do a manipulation task. So what you see here on the upper right, that is actually a kitchen from IKEA that we put in the lab. So this is in the lab that we want to use for research. And the idea long-term wise, of course, the kitchen you can imagine has the advantage that it can stand in for many other environments because it can represent any kind of challenge you can imagine, right? There is, of course, the basic pick and place kind of work. There is collaboration with humans. How do you understand humans? How can you collaborate with people? How can you manipulate non-rigid object, complex things, how liquids, granular media. So any of the challenges that we see often in industrial settings or even in healthcare settings or so, you can represent also as a kitchen challenge. So that was the main motivation for us to get started in the kitchen. And I'm gonna show you some of the work we've done, especially in this context. So here's an example. Here's the kitchen again. This is the robot we have. It's a mobile base. So you won't see any mobility. So we're really focusing solely here on the manipulator. But the first task sounds super simple, where we have a kitchen, we have a 3D model of the kitchen, which means we know the shape, articulation of the doors and drawers. We even have 3D models of the objects that you see here. These are from the YCB data set. I'm sure many of you have seen these. And we just want the robot to kind of move objects around, right, into hopefully desired target configurations. On the right-hand side, you can see that the main sensors we are using for perception are depth cameras. Okay, these are placed on the ceiling here, 2 of them. And we also did some work where we put a camera onto the gripper of the robot so that it can move around and gets a better view. But the first work is really focused mostly on these cameras. So what we use them for is to track the robot, to detect objects, and then also track things that are going on in the kitchen. Okay, so a larger scale manipulation system in this context, even for this reasonably simple task, already has to bring together several ingredients in order to solve these kind of problems. The first one is what we call task and motion planning, where the idea is, imagine you want to set the table and you have a goal configuration where the plates and the knives should go. And now the robot needs to plan where the knives are, how it can, for example, acquire the plate. It needs to take into account that in order to get the plate out of a cabinet, it first has to open the door of the cabinet so that it can reach it. So in task and motion planning, the reasoning is both at the higher, let's say, logical level of plan steps and preconditions, but also at the low level planning of how the robot can actually reach certain positions in the environment. I'm not gonna go into any details on this one today. Excuse me? Okay. Another important component is what we call state estimation and perception, where the robot uses, for example, these depth cameras in order to figure out what's going on, where the objects are the doors open or closed, and things like that. And then even if it, let's say, knows where the objects are, it needs to figure out how can it pick up the object. So what is the grasp location that is accessible to it, and that has a high chance of success in the sense of actually picking up the object. It needs to reason about where to put the objects. And finally, even when you know all of this, there's still the question of trajectory generation, which means how do we move the manipulator itself in order to achieve these goal configurations and while avoiding obstacles on the way. And each of these is actually in itself already a pretty complex, as you can imagine, research area, but I'll just give you some examples for the work we've done there. Okay. The first one, and I'm sure there's some connection to some of the talks you might have seen this morning already, is pose estimation, where the idea is if we have these 3D models of the objects and the robot should, for example, pick them up, then it needs to know the position of the object. So this is very much in what we might call a model-based kind of framework, where we say we have these object models, we estimate their positions, and then we can do planning with them. So just high-level idea is you have a model of an object. This is the Cheez-It box. Now you observe an image, and what you want to know is the position of that model in the scene. Okay, and in this case, it's a 60 object pose where we have the 3D translation, but also the 3D orientation. Okay, and typically this problem nowadays is of course addressed with deep learning, right? These are by far the most successful techniques these days. And standard approaches actually always aim at, let's say, taking in the image and then somehow regressing to a 60 pose estimate for the object, right? So image in, and then some techniques detect key points, or even avoid detecting key points and then immediately regress to a 60 pose. The limitation of that is actually that for many objects, there is no unique 60 pose that you can determine. Imagine you have a round bowl that has the same color around it. Then any rotation of the object, you cannot resolve which orientation the object is in. So it's not a true 60, unique true 60 pose. And for many objects, if they are partially occluded, you can also not determine the 60 pose. So what I want to give you an example for some work we've done where we're not aiming at a single pose estimate, but actually at a full distribution over the 60 pose space. Okay, so here's just some lines of work that we've pursued in this context. The two on the left are more in this tradition of regressing kind of to a 60 estimate. But again, today I want to focus on this work that's called pose RBPF, where we really want to estimate a full 60 pose distribution over the object. Okay, and as a result, that can naturally deal with symmetric objects as well. Okay, I'm also bringing up this example because I think it nicely combines kind of the benefits of deep learning with also then, let's call it, traditional Bayesian estimation techniques. Okay, so what we want to do is we want to first train a deep network that for a specific object, in this case, let's say we have a model of this, put a laser pointer here, of this, I think it's bleach or so, a bleach bottle. Okay, so we want to train a network that takes as input an image of the bleach bottle and estimates from which viewpoint we are looking at the bottle. Okay, so this is the orientation we are focusing in, right? Which means the orientation of the camera relative to the object, but it's also roll and pitch and yaw. So it's a three-dimensional orientation. Okay, so we want to train a network so that it can somehow extract that from an image. And this is based on work that Sundermeyer and colleagues published at ECCV. It was best paper that year, ECCV 18. How we can do this is the following. We have a deep network, a so-called variational autoencoder. You can see here the structure. It has this kind of typical bottleneck in the middle, which will become pretty important. Okay, and we train it by generating images of this model, of this object that you can see here on the left. And in simulation, we add a lot of noise and we randomize the position and everything, lighting conditions. We also have occlusions. And on the right side, the desired output for the network is a clean image of this object. Okay, so this is what the training data looks like. Okay, this is fully done in simulation. And then if we train the network after the first, let's say 200,000 views, it already can, based on the input, it can kind of generate an output that somehow resembles at least the desired target output. But if we keep on training, actually, ultimately, we're getting results that look actually pretty good. So which means that this network must have learned to take this noisy, occluded image and somehow recover the view onto the object. And since we're forcing this through this bottleneck, in this 128-dimensional vector in this case, somehow the network must encode the viewpoint onto the object because otherwise it wouldn't be able to reconstruct the image. Okay, that's the key trick. So we are really interested in this bottleneck embedding or encoding. Yeah. So now once we train the network to do this, we can throw away the decoder because we actually only care about the encoder. We can use this in the following way. Let's assume we have this object and we generate with 5-degree discretization, okay, around the object, in this case, almost 200,000 views onto the object. Okay, so this corresponds to discretization of the 3D viewing sphere. And then for each of these views, we can render the view. We can feed it through the encoder that we just trained. And now we have 200,000 vectors that somehow represent or encode the view. Okay. Now, if we get an image on the left, okay, with, let's say, somehow zoomed into the bounding box, we can feed that into the encoder. We get our vector. And now we just do a similarity measure between that and all the different views we have in our codebook. And we get some kind of matching score, right? So in this case, for example, this might be the most similar view onto the object according to the embedding that we learned compared to the image on the left. Okay, so this gives us, in a Bayesian context, you can turn this into a likelihood model, which means how likely is it to see this image giving a certain view onto the object. Now, if we want to use this for full pose estimation and tracking, we can feed this into a particle filter. I will not talk about any details about particle filter, but in this case, we have actually a so-called raw black-equalized particle filter, where we do the following. We represent the 6-dimensional distribution not by sampling in the 6-dimensional space, because that is extremely inefficient. What we do is the following. Each particle has a sampled XYZ position of the object, which is the translation, and a 3D distribution over the orientation. So pose XYZ is sampled, and the distribution over poses is computed as kind of a multinomial over the 3D viewing angles. How this works is the following. Imagine we have a particle like this one here. So the index I is for particle I. So it has a 3D translation and an orientation distribution. As you can see on the right, this is kind of the different views. With the translation, what we can do is we have an image and we know the camera parameters. So we can now use the translation to crop a bounding box around the object. Okay, different translations give us different bounding boxes. And then we can take this region of interest, feed it through the encoder, compare it with the code book that we learned for this object. And that now again gives us a likelihood over the distributions. And that is all we need to now run a full particle filter over the 6D space. Okay, we can do this also for tracking in the temporal context, where we have, again, typically, let's say we have 50 particles. Each particle has a translation. And importantly, each particle has actually about 200,000 possible orientations. Okay, so let me just give you one example what this then looks like. What you see in the upper part is the input image and the bounding boxes. Each bounding box corresponds to one particle. And you will also see the object kind of overlaid of the image according to the best estimate. And in the lower part, you will see kind of the viewing distribution onto the object according to one of the particles. So that represents kind of the orientation estimate for the object. Okay. On the left side, you will see the estimate if we only use color. On the right side, you see the estimates if we use color and depth. So you can see that we actually can track this object, the Cheez-It box in this case, pretty well. The system is very robust. In this case, actually, the Cheez-It box is occluded heavily by this drill that you can see now. You can see it actually better, but we can still track it well. Here is tracking a bowl that is symmetric. And if you look at the lower part, you can see that the viewing uncertainty correctly represents the uncertainty that we have due to the symmetry of that bowl. Okay. Here, this is for more industrial objects that are highly symmetric too. And you can see that the system actually at the time got state-of-the-art results on these kind of objects. Okay. The nice thing is we can do this in real time with 50 particles at 30 frames easily, because in the end, for every particle, the comparison with the viewing angle is just an inner product between these embedding vectors. And that can be done on a GPU all in parallel. Okay, so all of this works actually in real time very efficiently, and it's a full Bayesian estimation approach then. Towards the end, I think we'll also see, this can also do actually global localization. So this is not only useful for tracking, but we can also, if we don't know the object position at all, we can sample 3D particles in the space, and the orientation distribution then manages global uncertainty of orientations. Okay. So now that we can detect objects, we can also put this into a larger estimation framework that tracks also the kitchen cabinets and things like that. So I'm just going to show you one example here, where the robot now opens the cabinet. On the upper, you can see the robot operating. On the lower part, you can see from the camera point cloud, we are actually tracking the articulated model of the kitchen as well. So we keep track of where the robot is, we track where the doors and drawers are, and we use the technique that I just described you to estimate the object poses, which you can see here as well. So all of this is then done in a single optimization framework, actually. And with that, we can then do these kind of tasks like opening a cabinet and put an object in there. Okay, so this was focusing on the perception part. Now, another question is, of course, how do we move the manipulator? So the low-level control of that manipulator is actually pretty important. In this case, the goal is the following. So the robot we have for the arm, we have a certain target pose the gripper should reach to pick up an object, and we want to control the manipulator to this position while avoiding obstacles. And the technique we introduced here is a framework called Riemannian motion policies, and more recently, there's a framework called geometric fabrics. I encourage you to look at this, a tutorial on that out there that Nathan Ratliff gave at Call last year. But the key idea is the following. Imagine the robot, the tricky piece of this manipulator control is always that the control of the manipulator, even though the manipulator operates in a 3D space, the control happens in the degrees of freedom of the manipulator. In this case, the manipulator has 7 degrees of freedom, even though we're mostly interested in the 3D motion. There's a raised hand. If someone has a question? No? Should I keep on going, I guess?
Yeah.
I'll keep on going. Okay. So you'll just interrupt me if there's something in the chat or so I should be aware of. Okay. So we have this 7-dimensional control space, which is Q, and how we generate these motion commands now in these Riemannian motion policies is by defining points on the surface of the robot. You can see these points here on the right, but also which is now in the 3-dimensional state space. You can see them also here in the left image. And for each point, we can define local properties. For example, how far is the point away from the closest obstacle? Or we can also have properties like what is the direction to the goal? And with these properties now, we can generate accelerations for these points, which means each point specifies in which direction it wants to move. For example, in order to stay away from obstacles, but maybe also in order to go to the goal and things like that. And we can now collect all these local accelerations through this tree structure in order to generate control commands for the whole arm. Okay, here's an example now how this operates. This is Nathan in the background, and this is the robot where we track the cabinet using the depth camera. So we know the status of the cabinet. And the main goal is just to generate these reactive control commands for the manipulator. And in this case, the manipulator doesn't like open doors and drawers. So you can see that we are able to then generate these pretty natural real-time behaviors for this arm. Okay. We can also put this in the context of a more task and motion planning system. So here, for example, the task of the robot is to open the drawer and put this spam can into the drawer. And you can see that even if in this case, Chris kind of disturbs it, the robot is pretty reactive to this. So here it opens the drawer. We have on top of this a full task and motion planning system that also keeps track of the progress. So in this case, for example, Chris closed the drawer again, and the observer realized that a precondition that the drawer is open was violated, and then it goes back in the plan to establish that precondition again. So now it's opening it again, and then it goes back to picking up the spam. Okay, so this reactive controller is again now connected to a high-level planning system. So this is how we do control. Again, these are just some high-level ideas I provide you because of limitations of time. So far, we can do these tasks in a kitchen, pick-and-place tasks, but the key assumption was that we have models for everything, right? We needed to have the 3D models of objects so that we can do pose estimation and then pick up the objects. In this section, I want to briefly give you some idea of how we're moving away from this notion that we need models for these objects. Okay, how we can do this for unknown objects. One idea is if we have a physics simulator, we can first of all take object models, like in this case, this red object. We can sample many ways for grasping an object. And then in the physics simulator, we can shake it. And that way we can determine which grasp poses succeed at keeping a good grip on the object. I hope that idea makes sense. We can do this because it's on a GPU. We can do this with 1,000 grasps in parallel, no problem. Okay. And then what we get out of this is an object model that is annotated with relative grasp poses that work well for this specific object. Okay. Then Clemens now generated a pretty large data set on this, where he took from ShapeNet more than 8,000 objects. And each of these objects, as you can see here, is annotated with gripper poses that have a high chance of succeeding on these objects. We can now take this data set and train a deep network, okay? In this case, the first work we did was the 6 of GraspNet, where the idea is we train a network to take as input a point cloud rendered through the simulation, and the deep network is trained, it's a variational autoencoder again, such that it takes in the point cloud and generates samples for gripper poses that have a high chance of succeeding according to the data set that I just showed you. Okay, we can also refine these gripper poses with an additional network. In the interest of time, I'm not going to go there, that can refine these poses as well. Okay, all of this is then done through these deep networks that are trained on this large scale simulated data. And then we can go in the real world and it actually works surprisingly well. Okay, so this is where some of the first experiments we did. These are objects. First note that these shapes were not specifically in the data set the network was trained on. And also the network was not trained on real data. It was only trained on simulated data. Okay, and since we're using depth cameras, actually the data, it transferred actually very well. Okay, so we can now pick up unknown objects. We can also do more complicated tasks like object rearrangement, where you see the image on the top. Let's say this would be the target configuration for objects. And in the bottom, you see the current configuration. And we have a paper coming up at ICRA where the robot then learned to kind of take the scene on the lower one, on the lower scene, and move objects around such that they match the target image. Okay, and that network automatically does object segmentation. It matches across the scenes and also reasons about free space. So it even takes objects out of the way if the rearrangement requires that. So I encourage you to take a look at the paper. Okay, we can also use the same kind of techniques for object handover, where the human holds an object and the robot in real time then determines good grasp approaches for these objects. That's also a paper coming up at ICRA, the most recent one. And it turns out it's surprisingly complex how to do object handover. For us humans, all of this is so easy and simple, but for robots, it's still not a trivial or solved task. Finally, do I have maybe 5 minutes left, or how are we doing on time?
We're a little tight, but I think we can spare a few minutes to go over.
Okay, I'll very quickly just give you an idea. Again, you've seen already on this previous task a lot of work on where we leverage simulation. I just want to highlight a little bit more the simulation aspects. So here, for example, you can see our robot operating in one case in the simulated kitchen, in the other case in the real kitchen. And you must admit you have to look at least twice to figure out which is real, which is simulated, right? And that's just an idea of how close we can get now, right, in simulation to the real world. So which means we can generate simulators that are photorealistic, that are physically accurate, which means we can train our robots and our perception system in simulators that are, I'm not claiming that are perfectly accurate, but that are getting closer and closer, which I think is very promising. This is not only for kitchen, but this is work, for example, the Isaac SDK and simulation teams are working on. This is a collaboration with BMW. So now where we can go and really simulate complete manufacturing sites, factories, right? So here, all of this is physically realistic simulation. As you can see, a key trick is we still haven't really figured out how to do good simulation of humans and their behavior. Okay, but there's a lot of ongoing work, but I think this is also just pointing in an exciting direction, right? There, of course, we can train deep networks in simulation. And one notion is always that we can, if the simulation doesn't perfectly match the real world, then there's this notion of domain randomization. And we've done research on how we can estimate these randomization parameters so that the simulated controllers transfer to the real world. You can see on the right, it's this Pagan Hold task. And with that, I would actually like to thank you. And I think we've seen really good progress in robot manipulation on the perception side, on the control side and reasoning side. And I think a lot of that is really due to progress in deep learning and perception. And of course, it's only made possible through GPU-enabled computation. And I think that the next generation of robots, we will be trained primarily in simulation as these simulators become more and more capable and realistic, and as we figure out more and more ways of actually generating these assets in these environments in which we can train these robots. So there's still a lot of open research that has to be done, but I think we've made some very exciting progress. And I want to also highlight there are these different components. At Nvidia is developing Isaac Sim and Omniverse, which is this whole simulation environments and framework that is also specifically designed for robotics. And SDK is more geared towards an SDK for robot navigation and manipulation. And with that, I'll thank the team and thank you for your attention. And again, all the great interns we really work with on these projects. Thank you.
Thank you so much. And again, I'll clap virtually, right, for the attendees. Thank you for the wonderful presentation. We do have a few questions on the chat. I'm selfishly going to ask a question, not on the chat, regarding the humans part of the system. So it seems like there are a couple of scenarios we have humans, interacting with the manipulator, and then handing off, right? And so they're operating in close proximity, right, to the systems, but it didn't seem perhaps that they were modeled in any way. So can you comment on the human aspect?
Yeah, so this work, the main focus was also on, of course, the one thing is if you want to do this human object handover, right, perception is crucial. So we do tracking of the human and the hand, and then we need to segment the object from the hand so that when the robot wants to pick up the object, for example, first of all, it has to figure out how can I pick up the object in the first place? What is the good grasp? But also it needs to do so without squeezing the human hand, right? So it needs to find, so all we do, these parts we do with deep learning, and then in real time, it needs to generate the controls to go there. So there are various components that really have to come together for this. And I must admit, we're still not quite at the level where it's as fluent as you would like it to be, right? So one aspect is still, how can we get these robots to be fast enough so that people actually really see a benefit from working with them? Because humans are not very patient in waiting for the robot to move.
Absolutely. Maybe one more question for the chat. So here, the question that states, is there a performance trade-off when condensing the dimensions using an autoencoder architecture over using traditional CNN-based architectures?
Once again, sorry, I didn't, the first, again?
Let me say that again. Is there a performance trade-off when condensing the dimensions using an autoencoder architecture over using traditional CNN-based architectures?
Well, in this case, I think it depends on which part, right? Like for the pose estimation, the main idea was with a traditional CNN architecture, what you would typically do is you would just learn to regress, for example, to the 60 pose, right? And with the autoencoder, we really wanted to focus on an efficient representation of this orientation distribution. So that was the key trick. I think in general, in this whole domain, of course, one topic that keeps on coming up is contrastive learning, for example, right? Like we've done for object segmentation, we've looked at using contrastive learning techniques for robust representation learning, which I think is also a very exciting and promising direction. I mean, we've seen extremely good results coming from the vision and natural language community. It's still not, it hasn't been as successful in robotics, but I think this will come up also as we can generate more and more data.
Well, Dieter, we want to thank you again for being here and giving this wonderful talk. We have several other questions and then the Q&A feature, and I do hope you'll find the time to stick around a little bit and answer them via chat.
Should I just type them in the chat then?
Yeah, there's a Q&A option, and you should be able to answer some of these if you have the time.
All right, I'll do that.
Great,
Yes,
thank you so
for having
much.
me.
Thank you so much. And so in the interest of time, perhaps I'll again thank our keynote speaker and move on to the next